Hi, my name is Carlos Espino, and today I will be presenting performance of a refrigeration system using R-134a alternative refrigerants. This research was done under the supervision of Dr. Melanie Derby and Jordan Morrow. Refrigerants are working fluids used in a refrigeration cycle, such as an air conditioning unit or a refrigerator, but they also account for global warming damages. The United Nations work on developing agreements that will reduce the damages of global warming and climate change. Most recently, the Kigali Agreement plans to reduce the production and consumption of hydrofluorocarbons known as HFC refrigerants, but also looking for alternatives. One of the possible alternatives is hydrofluoroolefin or HFO HFC mixture refrigerants that have a lower global warming potential. Our objective is to find the advantages and disadvantages of HFCs and HFO HFC mixture refrigerants by looking at their cooling capacities and coefficient of performance. The cooling capacity is the amount of heat transfer energy required to cool down the system, while the coefficient of performance is the ratio of that cooling capacity divided by the work required to also cool down the system. With higher coefficient of performance, a system would be more efficient and it would require to run on less power energy, and therefore it would be cheaper to run. When looking at an experiment, we will be using R-134a, which is an HFC refrigerant that has a high global warming potential of 1300, and we're going to be comparing it to R-513a, which is an HFO HFC mixture that has a lower global warming potential of 573. Our refrigerants will run through a small-scale refrigeration cycle, which can represent a refrigerator or a window-type air conditioning unit. The main parts of the cycle are a condenser, an expansion valve, an evaporator, and a compressor. The refrigerant will start as a superheated vapor, and it will be subcooled into a liquid to then be superheated into a vapor again to repeat the cycle. The condenser will run at temperatures of 40 to 60 degrees Celsius, and the evaporator will run at temperatures of 15 to 30 degrees Celsius. Although we haven't been able to produce experimental data, we were able to make a theoretical analysis to compare both refrigerants. When looking at the graphs of the poster, the three on the left represent the coefficient of performance, while the three on the right represent the cooling capacity. All of the graphs have evaporator temperatures of 10, 20, and 30 degrees Celsius. The two at the very top represent condenser temperatures of 40 degrees Celsius. The two at the middle represent condenser temperatures of 50 degrees Celsius, and the two at the bottom represent condenser temperatures of 60 degrees Celsius. What we're able to see from the graphs is that R513A in orange has a lower coefficient of performance and lower cooling capacity than R134A in blue. We're able to see that the coefficient of performance decreased about a 16.8 to 20.1%, and the cooling capacity decreased at a 11.7 to 15.3%. Since R513A has a lower cooling capacity, in order to meet the coefficient of performance of R134A, it would be required to run on less power. And for a system to run on less power, other parameters will be affected, such as the mass flow rate and the heat transfer of the original system. Eventually, these changes will require physical changes to the equipment of the system, such as in the compressor and the heat exchangers found in the condenser and evaporator. What we can conclude is that moving to an alternative refrigerant, such as R513A, it will require a sacrifice in the system's performance, or it will require costly adjustments to the system. With this theoretical data, we can also make a hypothesis for our future experimental data, and that is that R513A will have lower coefficient of performance and lower cooling capacity than R134A.